Alright everybody, let's get into Chapter 17, Applications of Aqueous Equilibria. This chapter largely follows up on the previous chapter, so make sure you've seen those videos before watching this series. We saw how Bronsted acids and bases behave in Chapter 16. Now let's look at how they interact with each other. You'll recall from Chem 1211 that one of the most common reactions in aqueous solutions are acid-base neutralization reactions, which typically produce water and a salt as the products when an acid and base react together. The simplest cases are those where the reactants are a strong acid and a strong base. We can use the reaction here, between HCl and NaOH, as a representative example. These react to form water, and the salt is the ionic compound formed between the anion from the acid and the cation from the base. In this case, that gives us NaCl, sodium chloride. Strong acids and strong bases are both strong electrolytes, and sodium chloride is too, since it's a soluble ionic compound. If we, therefore, assume complete dissociation of these species and transform the equation into net ionic form, you'll get the reaction shown here, the reaction between hydronium ions and hydroxide ions to form two equivalents of water. Remember, when a strong acid dissociates an aqueous solution, it really produces hydronium ions, not simply H+ ions. Anyway, since the only net chemical transformation forms water, we effectively end up with a neutral solution, pH 7, after complete neutralization. You might also recall from first semester general chemistry that when we have a weak acid in a neutralization, we treat it as effectively a non-electrolyte. We saw in Chapter 16 that under most situations, weak acid dissociation only occurs to a very small extent, typically less than 5% at most. For instance, if we look at the neutralization of the weak acid, acetic acid, with sodium hydroxide, which we used as a strong base in the previous example, the net ionic version of this equation shows that the products are water and acetate ions. Since the latter is the conjugate base of acetic acid, a weak acid, they are themselves weakly basic. In other words, one of our products is weakly basic, so when neutralization is complete, the pH of the solution will be weakly basic or above 7. This can be seen if we use a phenolphthalein indicator to monitor the reaction. After neutralization, the indicator's pink color reveals that the solution has a pH above the color change point for phenolphthalein, so above 8.5 or so. The opposite situation can be seen in a strong acid-weak base neutralization. If, for instance, hydrochloric acid reacts with a weak base ammonia, we get ammonium chloride. As a weak base, ammonia is only partially dissociated in water, but HCl, a strong acid, and ammonium chloride, a soluble ionic compound, are both fully dissociated. Again, taking into account that the protons in aqueous hydrochloric acid exist as hydronium ions, the net ionic equation shows that the products of the neutralization are water and ammonium ions. The latter is the conjugate acid of the weak base ammonia, and hence is itself a weak acid. Hence, we have a weakly acidic solution after neutralization is complete. We can see this in action if we use the indicator methyl red to track the reaction. This indicator is yellow in neutral or basic solutions, but red in acidic ones. After the neutralization of ammonia with hydrochloric acid, we see the solution transform into a red color, revealing that it has an acidic pH. Finally, if we have a weak acid-weak base neutralization, only the salt produced will be completely dissociated, and the net ionic equation shows that we end up with both weakly acidic and weakly basic species. In this example, acetic acid and ammonia come together to produce ammonium ions and acetate ions. As discussed in the section on acidic and basic salts at the end of Chapter 16, you have to use the relative strengths of the acidity and basicity of the products to predict whether the solution will be acidic, basic, or neutral after neutralization occurs. If you think back to Chapter 15 and Le Chatelier's principle, you'll recall that changing the concentrations of reactants or products in an equilibrium reaction causes a shift in the position of that equilibrium to relieve the stress on the system. An important version of this for weak acid-weak base equilibria is what's called the common ion effect, where the position of equilibrium shifts upon addition of a substance that provides an ion in common with one of the ions already in the equilibrium. We'll consider the dissociation of the weak acid acetic acid into hydronium ions and acetate ions for the following examples. Consider the two solutions shown here. Both of these beakers contain an indicator called methyl orange, which is red at or below pH 3 and yellow at or above pH 4.5. The beaker on the right contains only 0.1 molar acetic acid, while the beaker on the left contains 0.1 molar acetic acid and 0.1 molar sodium acetate. The beaker with only the acetic acid has a pH of 2.89, while the pH of the acetic acid-sodium acetate mixture has a pH of 4.74. almost 2 pH units higher. Coming back to our equilibrium equation, we see that the acetate ion is involved in this equilibrium on the product side. Adding sodium acetate, a source of those acetate ions, to aqueous acetic acid will cause the dissociation equilibrium to move away from the products, or away from the dissociated ion side of the equation. Since less acetic acid remains dissociated, we have a lower concentration of the other product, hydronium ions. Fewer of these means a less acidic solution, of course, hence the pH difference in the two solutions from the previous slide. We can see on this slide that, as we would expect, increasing the concentration of acetate ions in 0.10 molar acetic acid causes a corresponding drop in the concentration of hydronium ions. Let's analyze this equilibrium situation mathematically. If the pH of a 0.10 molar acetic acid solution is 2.89, what is the pH of a solution that contains 0.10 moles of acetic acid and 0.10 moles of sodium acetate in enough water to produce 1 liter of solution? Initially, both our acetic acid and acetate concentrations are 0.10 mole divided by 1.0 liters, or just 0.10 molar. We can assume, as usual, that the 1.0 times 10 to the minus 7 molar concentration of hydronium ions in water prior to dissociation of the acid is negligible, and hence this is effectively 0 molar initially. Completing our ice chart, assuming dissociation of acetic acid, we can see that the concentration of acetic acid at equilibrium is 0.10 minus X, the acetate concentration is 0.10 plus X, and the hydronium concentration is approximately X. Plugging these expressions in for the concentrations in the Ka expression, and assuming that X is much smaller than 0.10, and hence that 0.10 plus X and 0.10 minus X are both still effectively 0.10 after rounding, we solve for our hydronium concentration, which turns out to be 1.8 times 10 to the minus 5th molar. Plugging this into the formula for pH provides a value of 4.74, almost 2 pH units less acidic than the 2.89 pH for a 0.10 molar solution of just the acetic acid. This common ion effect is responsible for the behavior of what are called buffer solutions. These are solutions that contain both a weak acid and its conjugate base in comparable concentrations. These are called buffer solutions because they resist rapid changes in pH if limited amounts of a strong acid or a strong base are added to them. The acetic acid sodium acetate example from the previous slides consists of both a weak acid and its conjugate base, and hence would behave as a buffer solution. The same is true for any mixture of a conjugate weak acid-base pair. Note that they must be conjugates, not just any mixture of a weak acid and a weak base. If we use the acetic acid acetate example and consider the dissociation equilibrium involving them, we can analyze what will happen if we add a strong base or a strong acid to a mixture of those two species. Adding a strong base, in other words a source of hydroxide ions, that will neutralize the acetic acid, which produces acetate ions as a product, hence adding to the concentration of the conjugate base already present. Conversely, adding a strong acid will result in neutralization reaction between the added hydronium ions and the conjugate base component, converting some of the acetate ions into acetic acid. In this case, this ends up increasing the conjugate acid concentration, since there was some acetic acid already present in the mixture of these two substances. The solutions shown here demonstrate how this gives rise to the behavior of buffer solutions. A dilute hydrochloric acid solution with a pH of 4.74 can be completely neutralized by addition of just a small amount of sodium hydroxide solution. On the other hand, our solution with 0.10 molar concentrations of both acetic acid and sodium acetate also has a pH of 4.74, but even adding a much more significant amount of, say, sodium hydroxide solution results in very little change in the pH, as evidenced by the absence of any color change of the indicator. This graphic does a good job of representing what happens in a buffer solution. We start with a mixture of a weak acid and its conjugate base, the middle bar on this slide. If we add some strong acid, we'll convert some of the conjugate base into the weak acid as a result of the neutralization, but we still have a solution with both the weak acid and the conjugate base pair present, so the pH doesn't change much. Likewise, adding a strong base will convert some of the weak acid into the conjugate base component, but we still end up with a mixture containing both substances, and hence the pH of the solution changes only very little. An important assumption here is that addition of either strong acid or strong base occurs to an extent that doesn't completely neutralize either the acidic or basic components of the mixture. If either the weak acid or its conjugate base are completely neutralized via the addition of a strong base or a strong acid respectively, we would no longer have a mixture of the two substances, and hence we would lose the buffer characteristics. There's an equation, the Henderson-Hasselbalch equation, that allows us to calculate the pH of a buffer solution. By rearranging the expression for Ka for a weak acid dissociation, and subsequently converting hydronium concentration to pH, followed by some rearrangements based on the properties of logarithms, we get the equation highlighted here. The pH of a buffer solution is equal to the pKa of the weak acid component, plus the base 10 log of the concentration of the conjugate base divided by the concentration of the weak acid.